Have you ever wondered why you can remember the past, but never the future? Why a shattered glass never jumps back onto the table? Physics doesn't forbid it. The laws work perfectly in reverse. So why does the world seem to have a direction? The answer isn't time itself. It's something far stranger, something invisible that shapes every moment of your life, entropy. And once you understand it, you realize the universe isn't just ticking forward, it's being guided by probability, not destiny. If you take physics seriously, really seriously, you very quickly run into a strange and uncomfortable fact about time. We all experience time as something that moves relentlessly forward. Yesterday is gone, tomorrow hasn't arrived, and now is always slipping away. This feels so obvious that we rarely question it. But when you open the book of physics and look at the actual laws that describe how nature works, that sense of direction almost completely disappears. Most fundamental physical laws do not care which way time flows. Newton's laws of motion work just as well if you replace time with minus time. If you filmed 2 billiard balls colliding on a table and then played the film backward, the motion would still obey Newton's equations perfectly. Nothing would look illegal or suspicious. The same is true for the equations that govern electricity, magnetism, and even much of quantum mechanics. At the microscopic level, nature does not carry a label that says past or future. This creates a deep puzzle. If the laws themselves make no distinction between forward and backward time, where does our strong sense of direction come from? Why does the world around us behave so differently depending on which way time goes? A broken cup never leaps back onto the table. Heat flows from hot objects to cold ones, and smoke spreads out instead of gathering itself neatly. These processes clearly have a preferred direction, yet the basic laws underneath them do not. The key insight is that the arrow of time is not written into the laws of motion. It emerges from something else entirely. When physicists first noticed this mismatch, it was deeply unsettling. We had equations that were time symmetric, but a world that clearly was not. This meant that time's direction was not fundamental in the way space or energy is fundamental. It had to be an emergent feature, a consequence of how large collections of particles behave together. Consider a simple example. If you watch a single molecule bouncing around in a box, there is nothing about its motion that tells you which way time is going. Reverse its velocity, and it behaves just as naturally. But when you put trillions of molecules together, new patterns appear. Gas spreads to fill a room. Heat equalizes. Order dissolves into disorder. These are not new laws being added. They are the statistical result of many particles obeying the same time reversible rules. This is where people often make a mistake. They imagine that time must be pushing things forward, forcing the universe to age and decay. But time itself is not doing the work. The laws simply allow many possible behaviors, and when vast numbers of particles are involved, some behaviors are overwhelmingly more likely than others. The universe follows probability, not preference. If time were truly fundamental in the sense we feel it, we would expect the equations of physics to forbid backward processes. They do not. Nothing in the equations says a shattered glass cannot reassemble itself. It's allowed. It's just so fantastically unlikely that you will never see it happen. The difference between possible and probable is everything here. So the first key realization is this: the direction of time is not enforced by the laws of physics. It is not a built-in rule of nature. The equations are neutral. They are indifferent. They describe motion without caring about past or future. That realization changes how you think about reality. Time stops being a cosmic river, carrying everything along, and starts looking more like a shadow cast by deeper processes. What we call the flow of time is something we infer from irreversible changes, not something the universe explicitly commands. Once you accept that the laws themselves are time blind, the real question shifts. It is no longer, why does time move forward? But why do we live in a universe where forward-looking processes dominate? That question leads directly to entropy and probability, not to time as a fundamental force. In other words, time feels real and directional, not because the universe insists on it, but because the underlying rules quietly allow it, and statistics do the rest. When people first hear the word entropy, they often imagine it as some mysterious force that pushes the universe toward chaos. That picture is misleading. Entropy is not a force, and it doesn't push anything. It is simply a way of describing how many possible arrangements a system can have. Once you understand that, the direction of time starts to make sense without invoking anything magical. Consider a very ordinary situation. Take a box divided into two halves, with all the gas molecules initially trapped on one side. When you remove the divider, the gas spreads out and fills the entire box. No one finds this surprising. But if you think about it carefully, the reverse process is not forbidden by the laws of motion. Every molecule could, in principle, just happen to bounce in such a way that they all gather back on one side. The equations allow it. It just never happens. Why not? Because there are vastly more ways for the gas to be spread out than for it to be confined to one side. The spread out state has high entropy. The confined state has low entropy. When the divider is removed, the system moves from a rare arrangement to a common one. Not because time tells it to, but because probability makes it almost inevitable. This is the crucial point. Entropy gives time its arrow, not by commanding the universe to move forward, but by making forward motion overwhelmingly likely. When entropy increases, systems move into states that can be realized in more ways. Once there, they are extremely unlikely to wander back into more ordered configurations. Now scale this up to the entire universe. Everything around you, the air, the stars, your body, your brain, is made of enormous numbers of particles. When these particles interact, the same statistical logic applies. Energy spreads. Temperature differences even out. Structures decay unless energy is constantly supplied to maintain them. This universal trend toward higher entropy defines what we call the forward direction of time. Notice something important here. The arrow of time is not built into individual interactions. A single collision between two particles does not increase entropy in any meaningful sense. Entropy is a property of collections, not individuals. It only becomes relevant when you are dealing with large numbers of particles and coarse, grained descriptions, where you stop tracking every detail and start talking about general patterns. This explains why time's arrow is so robust at everyday scales, but almost invisible at microscopic ones. At the level of atoms, reversibility dominates. At the level of cups, clouds, and galaxies, entropy dominates. The arrow of time emerges only when you stop caring about every microscopic detail, which is exactly what we do as human observers. Another subtle point is that entropy does not say that order cannot exist. Ordered structures like living organisms, crystals, or machines can and do form. But they form only by increasing entropy elsewhere. A refrigerator creates order inside by dumping heat into the room. Life maintains its structure by consuming energy and increasing the entropy of its surroundings. The arrow of time is never violated, it is merely redistributed. In this way, entropy quietly governs the direction of every process you observe. You don't see cream unsteering from coffee, not because it breaks a law, but because it would require an absurdly precise coordination of trillions of molecules. The universe does not arrange itself so delicately. So when we say entropy gives time its arrow, we are not saying time is caused by entropy in a direct, mechanical sense. We are saying that entropy explains why one direction of time is statistically favored over the other. The future is the direction in which entropy is higher. The past is the direction in which it was lower. Once you accept this, time stops looking like a mysterious river flowing through reality and starts looking like a statistical gradient. We move forward. In time, the same way a ball rolls downhill, not because it must, but because going uphill would require an extraordinary coincidence. Entropy doesn't care about clocks. It doesn't care about calendars. But by quietly favoring disorder over order, it draws an arrow through the universe, and we call that arrow time. The reason the past feels solid and real, while the future feels vague and uncertain, has nothing to do with human psychology or consciousness. It is not because the mind is wired that way, and it is not because memory points backward by accident. The asymmetry between past and future is built into the physical world itself, and the key difference between them is entropy. The past is special because it was more ordered than the present. At every moment, the universe moves from states with fewer possible arrangements to states with many more. That movement leaves behind traces. These traces are what we call records. A footprint in sand, a photograph, a written sentence, a fossil in rock, or a memory in the brain are all physical systems that exist only because entropy increased somewhere else in the process. To store information, you must pay an entropy price. When your brain forms a memory, chemical and electrical changes occur. Energy is used. Heat is released. Disorder increases in the surrounding environment. The memory exists because the total entropy of the universe has gone up. There is no way around this. Information cannot be recorded without increasing entropy somewhere. This is why we have records of the past, but not of the future. The future has not yet undergone the entropy increase required to create those records. A photograph of tomorrow cannot exist today because the physical processes that would create it have not yet occurred. This is not a limitation of imagination. It is a limitation imposed by physics. If you think about it carefully, this explains why the past feels fixed and the future feels open. The past is fixed because it has already left behind physical evidence. That evidence constrains what could have happened. The future, on the other hand, has left no traces. Without records, there is nothing to anchor it. It remains a set of possibilities rather than a settled fact. Even our sense of causality is tied to this. Causes come before effects because effects involve entropy increases that leave records. You see the shattered glass after it breaks, not before, because the breaking process increases entropy and leaves debris, sound waves, and microscopic damage that serve as evidence. There is no equivalent trail pointing backward from the future. People sometimes ask whether the past still exists. In a strict physical sense, the answer is subtle. The past is not preserved as a clean, intact copy of what once was. It exists as information that has been dispersed diluted, and mixed into the present state of the universe. The molecules that once formed a cup are now scattered. The energy that once made a sound is now heat. The information is still there, but it is scrambled beyond practical recovery. This scrambling is another consequence of increasing entropy. As entropy rises, information spreads out into correlations among enormous numbers of particles. To reconstruct the past perfectly, you would need to know the exact state of every particle in the universe. Not only is that impossible in practice, it is forbidden by the very processes that increased entropy in the first place. Memory, then, is not a window into a special dimension called the past. It is a physical structure built in the present, shaped by irreversible processes. Your brain does not store the past because time points backward. Time points backward in your experience, because entropy made memory possible only in that direction. The future feels unreal because it has not yet been written into the physical state of the world. There are no fossils from tomorrow, no photographs from next year, no scars from accidents that have not happened. Reality feels asymmetric because the universe itself is asymmetric in how it stores information. So the past is not more real because it exists somewhere else in time. It is more real because entropy has already done its work on it. The future will feel just as real when entropy has increased enough to leave its marks. What we call the passage of time is inseparable from the creation of records. Without entropy, there would be no memories, no history, and no sense of before and after. The past feel because it is written into the present by disorder. And once written, it cannot be erased. Time feels like the most solid feature of reality. It marches forward, carries causes into effects, and never seems to hesitate. We schedule our lives around it, measure it with extreme precision, and assume it must be one of the universe's basic ingredients. But when you strip the problem down to its essentials, time begins to look less like a fundamental force and more like a consequence of something deeper, probability acting on enormous numbers of particles. At the microscopic level, the universe is not concerned with past or future. Individual particles obey simple, reversible rules. They collide, scatter, exchange energy, and move on. Nothing in those interactions demands a preferred direction of time. If you could track a single particle in isolation, you would not be able to tell which way time was running just by looking at its motion. The illusion of time's arrow appears only when you consider systems with vast numbers of particles. When many particles interact, some arrangements are extremely rare, while others are overwhelmingly common. This imbalance is not subtle. It is enormous. A highly ordered state represents an almost infinitesimal fraction of all possible configurations. Disordered states dominate simply because there are so many more of them. Probability takes over at this scale. A system does not move toward disorder because it wants to, or because time pushes it there, but because wandering into a more disordered state is vastly more likely than wandering into a more ordered one. Once you understand this, the apparent inevitability of time's direction stops looking mysterious. It is not enforced by a cosmic rule. It is enforced by statistics. The universe began in an extraordinarily special condition. For reasons we still do not fully understand, the early universe had very low entropy. It was highly ordered compared to what was possible. That initial condition set everything in motion. From that moment onward, the universe had one overwhelmingly probable direction to evolve toward higher entropy. That single fact is enough to generate the entire arrow of time we experience. What we call the future is simply the set of states with higher entropy than the present. What we call the past is the set of states with lower entropy. Time itself does not distinguish them, probability does. The flow of time is not a fundamental ingredient of the universe, but a label we attach to this statistical progression. This also explains why time feels unstoppable. Once a system moves into a more probable state, returning to a less probable one would require an extraordinary coincidence. It is not forbidden by physics, but it is so unlikely that it never happens on any human timescale. The universe does not remember how it got to its current state in enough detail to reverse the process. Because of this, time feels like destiny. But destiny is the wrong word. What we are really witnessing is the consequence of starting from a very unlikely state and then letting probability do its work. There is no goal, no plan, and no built-in direction, just overwhelming likelihood. This realization changes how you think about reality. Time stops being the master variable that controls everything else and becomes a useful way of describing change. What is truly fundamental is the statistical behavior of matter and energy. Time is the bookkeeping system we use to keep track of that behavior. When we say entropy broke time, we are really saying that entropy exposed time as an emergent phenomenon. Time feels deep and mysterious because we experience it from the inside, but from the outside it is just what large systems do when they move from rare states to common ones. In the end, the universe is not driven forward by time. It is driven forward by probability. Time is the story we tell ourselves to make sense of that motion. And once you see it that way, time stops looking like a law of nature and stops looking like a remarkably persistent illusion, one built from statistics, not destiny.